Let's continue talking about the 6.7 handout. We're on page 2 now, so I'm continuing along with my handout on 6.7. In this segment, we'll talk about the second and third pages. And let's look at example 3. Here's another example of an abstract inner product. Consider the vector space P2 polynomials of degree less than or equal to 2. And I just happen to write down here two typical members of P2, two elements in P2. When I write P of t equals at squared plus bt plus c, Q of t equals dt squared plus et plus f, I mean that a, b, c, d, e, f are real numbers, are specific real numbers. So I'm just trying to represent elements of P2 in general, but for a specific element of P2, those coefficients are going to have to be actual real numbers. And so I'm going to define this inner product. The inner product of P and Q is P evaluated at 0 times Q evaluated at 0 plus P evaluated at 1 times Q evaluated at 1 plus P evaluated at 2 times Q evaluated at 2. So it's kind of looks like a dot product kind of sum, but why am I using these evaluated at 0, 1, and 2? In a way, for this example, I just randomly picked 0, 1, and 2. I really could have picked any values of the input to get started here. But let's just work with this one particular example. And our question is PQ an inner product on this vector space? Let's check the properties. Now, before we check the properties, though, I want to just talk a little bit more about what this example looks like. Let's actually look at a couple very specific polynomials. So I wrote this down ahead of time. I just happened to pick P of t equals 3t squared minus 2t plus 1. And for Q of t, I picked t squared minus 6. So these are two elements of that P2 vector space. To compute this new inner product, I have to evaluate P of 0, P of 1, P of 2. That just means I plug in for t, and P of 0 turns out to be 1, P of 1 is 2, P of 2 is 9. And I do the same thing with Q. Q of 0 is negative 6, Q of 1 is negative 5, Q of 2 is negative 2 when I plug in. So for these two particular polynomials, P and Q, the inner product of P and Q, according to this rule, is P0, Q0, or 1 times negative 6, plus P1 times Q1, or 2 times negative 5, or P2 times Q2, which is 9 times negative 2. And when I figure that out, I get negative 34. Notice that the inner product can be negative. I know sometimes students get a little confused here and think, well, wait, doesn't that have to be positive? And an inner product can be negative. The positive business is only when you take the inner product of a vector with itself. So just notice from this example I'm working with, if I took the inner product of P with itself, the same P in this example, I get positive 86. And even that Q polynomial where I had those negative values, if I take the inner product of Q with itself in this example, notice that I plug in these negatives, but I'm squaring negative 6, squaring negative 5, squaring negative 4. So I end up adding three positives together, and I get a positive result. Let's go back to this handout then, the main handout, and start verifying the properties. Now, property 1 is that commutativity property, so we have to look at the inner product of P and Q and P. And when I wrote them out in this way, I didn't actually plug into those polynomials I described in this abstract way with coefficients a, b, c, d, e, f, because we don't need the a, b, c, d, e, f yet here. We can just write this out in this way. We can see already that the inner product of P and Q and the inner product of Q and P are the same, right? Just because of the commutativity and multiplication of numbers. Let's go on to property 2. That's that distributive property. And this is actually very easy to verify here too. It's kind of a mess to write down. I introduced a third polynomial r. So I have the inner product of p plus q and r. And so p plus q evaluated at 0 is just p of 0 plus q of 0. So I have p of 0 plus q of 0 times r of 0 plus p of 1 plus q of 1 times r of 1 plus p of 2 times plus q of 2 times r of 2. And again, because of being able to distribute through multiplication of numbers, I can rewrite that in this way. I'll let you read that on your own. And if I rearrange the terms, I can group these three terms first, which is just the inner product of p and r. And these three terms last was the inner product of q and r. So we see that that second property of inner product is satisfied. Now let k be a scalar. I don't know why I picked k instead of c here, but I did. I picked k. And let's look at what happens when I try to take the inner product of kp with q. So kp evaluated at 0 is just kp of 0. Kp evaluated at 1 is kp1. Kp evaluated at 2 is kp2. So when I plug into my formula, I get this. And that's an expression in real numbers where I can factor the k out in front of what looks just like the inner product of p with q. So the third property is satisfied. Now we're going to go ahead and verify the fourth, which is always just a little bit more complicated. What happens if you take the inner product of a polynomial with itself? Well, we already saw from our examples, we're going to get a square plus a square plus a square. So it doesn't matter whether the values of p of 0, p of 1, p of 2 are positive or negative, because we end up adding up the squares according to this rule. We're always going to get a quantity that's greater than or equal to 0. So the first part of property 4 is verified. But there's a second part to property 4. We still need to show that the inner product of a polynomial with itself is 0 if and only if it's the 0 polynomial. And by the 0 polynomial, I mean the function p of t that's equal to 0t squared plus 0t plus 0. So let's just think about what this would mean if the inner product of p with itself is 0. Then p of 0 squared is 0. I'm sorry, p of 0 squared plus p of 1 squared plus p of 2 squared is 0. A sum of squares has to be equal to 0. The only way that could happen is if all three of p of 0, p of 1, and p of 2 are all equal to 0. So this is a little bit subtle, right? We're saying we don't know we have the 0 polynomial yet. All we know is that we have a polynomial where these three values come out to be 0. So now I am going to actually plug into this general form of p of t, at squared plus b of t plus c equals 0. Because what does this tell me about what that polynomial p has to be? Well, let's see what that says. That says if p of 0 is 0, if I plug into this general form, I get c is equal to 0. Okay, c is 0. If p of 1 is equal to 0, if I set t equal to 1, I get a plus b plus c. That has to be 0. And if I set t equal to 2, so t squared is 4 then, and I get 4a. T is 2, so I get plus b times 2, or 2b plus c equals 0. So I get this third equation. I actually have three equations and three variables, and it's a system of equations that I can actually solve for a, b, and c. And it's very easy to solve for a, b, and c there. What you're going to find out is that not only is c equal to 0, but a and b must also be equal to 0. This system has a unique solution, and the solution is just 0, 0, 0. So that turns out that the only way the inner product of a polynomial with itself can turn out to be 0 is if it actually is the 0 polynomial. And I just noticed I have a little bit of a typo here. It's 0t squared plus 0t plus 0 is the 0 polynomial. And conversely, if you start out with the 0 polynomial, it's easy to verify that the inner product with itself is 0. So we have verified the four properties for that situation. Now there's one more example here that I want to get to in this handout, and example 4 may seem like the weirdest one of all for you guys, but we're going to go back to this vector space, of continuous functions on a closed interval, and I just happen to choose the closed interval from 0 to 1 here, that we've already denoted C of 0, 1. So the vectors in this vector space are functions, right? Continuous functions. So suppose f and g are two functions in this vector space. I'm going to define an inner product in this way. I'm actually going to compute an integral from 0 to 1 of the function f times the function g. And it seems strange, but we can actually verify that this definition satisfies the four properties, and that's what we're going to go ahead and do now. Property 1, the commutativity property, it's very easy to see that because if I take the integral of f times g, that's clearly the same as the integral of g times f, right? If I interchange those two, because multiplication is commutative. Let's go on to the second property here. And so this is that distributive property. I need a third function here. I'm calling the third function h. So the inner product of f plus g times h would be the integral from 0 to 1 of f plus g function times the function h. But f plus g is just f of x plus g of x. So inside the integral, I have the sum of two functions times h. I can distribute. Again, I'm using just distributing of real number values here. So I get the integral from 0 to 1 of f times h plus g times h dx. And because the integral of the sum of two functions is the sum of the integrals, I can take that apart as two separate integrals. And that's just the inner product of f and h with the plus the inner product of g and h. So there, property 2 is verified. Property 3, that's that scalar multiplication. So I'm going to use c times the function f for my first function. And here I get cf just by multiplying the function f by c, right? So I have this scalar multiple inside the integral that I can pull out in front of the integral sign. So it's that property of integrals that allows me to observe that I have c times the inner product of f and g. Third property is verified. Fourth property is a tricky one. I know I talk about this. I think I do talk about this property in the lecture video. So I'm going to be very brief here. I'm just going to run over it quickly and watch the classroom video if you want to see me talk about this a little bit more. But first we got to verify that the inner product of a function with itself is always greater than or equal to 0. Now, if you notice, we're integrating from 0 to 1 the function squared dx. Well, because we're squaring a function here, f of x, the values of f of x squared are always going to be greater than or equal to 0. I don't really write out much of an explanation here. I just sort of say done. But if you integrate a function that's always greater than or equal to 0 from 0 to 1, its integral, and really on any interval at all, is going to be greater than or equal to 0. So it's kind of obvious that that's got to be true. It's a little harder to show that the inner product of a function with itself is 0 if and only if the function is actually equal to 0, meaning the constant function 0. And so, you know, suppose that the function is not 0 for some x. So suppose we don't have the 0 function. Then when you square that function, you're going to have a positive number, so strictly positive, for some value of x. And because the function is continuity, that function is going to be positive over some interval, some subinterval of values in 0, 1. But because we're integrating the function squared, it can never dip below the x-axis. So once you have a little piece of the graph above the x-axis, the integral has to be positive. So we're basically saying that if the function is not always 0, the integral has to be positive, and that's kind of equivalent to saying that if the integral is 0, the function has to be the 0 function for all x in 0, 1. And so that fourth property is verified. So I'm going to stop here because the rest of this handout is on the classroom lecture.